A powerful solar storm can mess up life on Earth in a catastrophic way. It can leave huge regions of our planet without power, disrupt communication and navigation satellites, damage power grids and data centers. Scientists warn that the next major solar storm could become one of the most devastating natural disasters. And the question isn't if it happens. The correct question is when. And the scary part? This kind of weather doesn't happen in Earth's atmosphere at all. It starts 93 million miles away on the Sun. When the Sun becomes active, we can feel it on Earth. This activity can mess with satellites, GPS, radio signals, and even parts of the power grid. Scientists usually group space weather into three main types: radio blackouts, geomagnetic storms, and radiation storms from the Sun. Each one has a different effect on Earth. Radio blackouts happen when the Sun sends a powerful burst of energy, aka a solar flare, our way. When that energy reaches Earth, it hits the upper atmosphere and disrupts the way radio signals travel. Geomagnetic storms are different. Sometimes the Sun launches enormous clouds of superheated gas into space. These eruptions are called coronal mass ejections. Imagine billions of tons of solar material blasted away from the Sun at a speed of millions of miles per hour. If one of those clouds comes across Earth, it slams into our planet's magnetic field at full speed. The result is a massive geomagnetic storm. We've already seen some serious space weather recently. For example, in May 2024, the strongest space weather event since 2003 hit Earth. GPS systems went through massive disruptions. The US agricultural industry was hit hard, all because modern farming needs satellite navigation to work properly. As for the infamous 2003 event, it completely cut power in parts of Sweden and South Africa. You might be wondering, what will happen if we get something even bigger? Scientists decided to figure out what a true worst-case space weather event might look like. Now, worst case doesn't mean a once-in-a-million-year disaster. Planning for something that rare isn't super useful. Instead, researchers focused on events that could realistically happen once every 100 to 200 years. Rare, but not impossible. When a strong geomagnetic storm hits Earth, it doesn't just affect space. It can actually generate electric currents in the ground too. And since power lines are excellent conductors, those currents can get inside the electrical grid. It's like extra electricity getting suddenly injected into a system that wasn't designed to deal with it. If the currents are strong enough, they can overload parts of the grid. Safety systems may automatically shut sections down to prevent damage, potentially leading to massive blackouts. Whole regions might stay without electricity. But losing power isn't even the worst part. The extra current can also damage transformers, those massive machines that help move electricity across the grid. Some of these transformers weigh hundreds of tons and can take months or even years to replace. This means that even after the storm is over, parts of the electrical network may still remain damaged for a long time. The power grid on Earth isn't the only thing at risk. A serious space weather event will first mess with satellites hundreds of miles above our heads. And we depend on satellites far more than most people realize. They help us navigate, forecast the weather, communicate with relatives and friends all over the world, and track ships and aircraft. During a bad solar storm, many of those satellites could run into serious trouble. One problem is radiation. When the Sun throws large amounts of energetic particles into space, those particles can slam directly into spacecraft. Over time, they can damage electronics and slowly wear down solar panels, shortening a satellite's lifespan. During an especially powerful event, some satellites could fail completely. But there's another huge problem. A solar flare can actually heat Earth's upper atmosphere. When that happens, the atmosphere expands outward and becomes slightly thicker at altitudes where many satellites orbit. The change is tiny, but for satellites, it matters a lot. Imagine riding a bike on a smooth road, and then suddenly someone pours a thin layer of mud over it. You can still move forward, but you'll slow down faster than before. Something similar happens to satellites. The thicker atmosphere creates extra drag, and that drag slowly pulls satellites into lower orbits. If they lose too much altitude, some spacecraft can fall back into the atmosphere and burn up. And it's happened before. In 2022, solar activity caused Earth's atmosphere to expand right after a batch of Starlink satellites was launched. Around 40 of them couldn't maintain their orbits and eventually re-entered the atmosphere. But during a real worst-case solar storm, the situation could become way more dramatic. It could also prevent us from tracking satellites and increase the risk of their collisions with space debris. The next problem is radio signals. Right now, they're constantly passing through the air around you. Your phone, GPS, Wi-Fi, aircraft communications, ship navigation systems, emergency services, all of them depend on radio waves. And a bad solar storm can mess up many of those signals. Solar flares produce bursts of radio energy, and sometimes those bursts become so powerful that they drown out weaker signals on Earth. It's kinda like trying to hear someone whisper while a jet engine is running nearby. None of this means that a giant solar storm would send us back to the Stone Age. Even a worst-case event probably wouldn't be a Hollywood-style apocalypse. But it could create a chain reaction of problems. Satellites could fail. GPS could become unreliable. Flights could be cancelled. And parts of the power grid could be damaged. That's exactly why scientists spend so much time studying space weather. And now, they might have to come up with a pretty cool idea for protecting Earth from powerful solar storms. They proposed something called Storm Wall. The idea is simple. What if we don't just wait for solar storms to hit and deal with the damage? What if we weaken the solar storm before it reaches Earth? The idea is based on Earth's magnetic field. Our planet is surrounded by a giant magnetic bubble called the magnetosphere. It's like an invisible shield that helps protect us from charged particles coming from the sun. Researchers noticed that Earth's atmosphere already helps strengthen this shield. Tiny particles escape from the atmosphere and interact with the outer edge of the magnetosphere. So scientists decided to try to boost that process on purpose. Their plan involves 6 spacecraft orbiting Earth. Each spacecraft would carry materials like barium or lithium. If you release them into space, sunlight would charge those materials, turning them into a cloud of plasma. Plasma is basically a gas whose particles carry electric charges. The sun itself is mostly made of plasma. The idea is that those artificial plasma clouds would form near the edge of Earth's magnetic shield, and when a solar storm arrived, the plasma would help absorb, redirect, and weaken some of the storm's energy before it reaches Earth. According to the team's simulations, the system could reduce the strength of a serious geomagnetic storm by 50%. That would be a really great result. A storm that's cut in half would mean less damage to satellites, fewer communication problems, fewer GPS disruptions, and less stress on power grids. Of course, this is still just a concept. Nobody has built the storm wall yet. Nobody even knows for sure whether it would work exactly as planned in the real world. But the researchers say that the physics behind it checks out. And apparently, modern rockets can indeed launch the equipment we'd need for such a mission. There's just one problem, and it's money. Building and launching 6 spacecraft wouldn't be cheap. Plus, once the material is released into space, it's gone. You can't collect it, refill it, or use it again. The researchers believe that the mission would use about as much material as a dozen large tanker trucks. That's why the price of a truly massive solar storm could be exorbitant.
On July 23, 2024, Europe's Solar Orbiter spacecraft observed a super-powerful solar flare erupting from the far side of the Sun. This flare wasn't the most extreme ever recorded, but still, we got extremely lucky this time not to get fried by it. Such solar flares often cause long-lived, raging radiation storms, and if such a storm moves in the direction of Earth, it can lead to worldwide blackouts. Before we go deeper into details of that potentially disastrous solar flare, we need to figure out what exactly this solar phenomenon is. Solar flares occur because the magnetic fields in the atmosphere of our star are moving non-stop. When the Sun is approaching its solar maxima, and that's the most active period of its 11-year-long cycle, which is, by the way, exactly what's happening now, its magnetic fields get more and more tangled, making our star look like an enormous ball of tangled rubber bands. They loop around, cross over one another, cut one another off, and then reconnect. Ever seen iron filings sprinkled on a bar magnet? These filings line up along the magnetic lines of force. Like that, the hot plasma on the surface of the Sun is at the mercy of the magnetic lines of force. Sometimes, when the magnetic fields interact with each other, some plasma gets disconnected from the fields, and its particles accelerate to immense speeds and send powerful radiation to space. That's what a solar flare is. Other times, our star throws off massive amounts of matter. Those events are coronal mass ejections, CMEs. Just one CME can contain as much as 20 billion tons of material. If that material were rock, it would create a mountain about 2.75 miles across and almost a half a mile tall. The ejected material often travels at a speed of over 1,000,000 miles per hour. Solar flares and CMEs are the most powerful explosions in the solar system, releasing unimaginable amounts of energy. Solar flares have their own classification according to their strength. The smallest and weakened ones are A and B class. Then there are C and M class solar flares, and the strongest are X class flares. A number from 1 to 9, and in some cases a larger one, accompanies each letter. That's similar to the Richter scale for earthquakes. A and B class flares are too weak to affect our planet. As for C class flares, they may have small, noticeable consequences. M-class flares can cause short radio blackouts at the poles and weak radiation storms that can still harm astronauts. But the most dangerous of them all are X-class flares. These are flares more than 10 times more powerful than X1. That's why the classification of X-class flares can go higher than 9. Now let's get back to that recent solar flare. It was X14 Class 1. Now, we already know that it means it was an extra strong flare. Other large flares astronomers have detected recently include an X12 solar flare that happened on the 20th of May and an X10 flare that occurred on the 17th of July. All of them have come from the backside of the Sun. If we talk of the Earth side of our star, the largest solar flare that has been recorded so far within this solar cycle happened on the 14th of May. It was an X8.7 flare that led to radio blackouts, and a strong geomagnetic storm leading to magnificent auroras all over the world occurred a few days earlier. Powerful coronal mass ejections accompanied this storm. As for the July X-class flare, it was so powerful that it could have ended up tragically for us. Luckily, all that magnetically charged plasma blast that accompanied the flare didn't travel in our direction. If it had, it would have been quite the solar storm. Auroras would have been incredibly impressive and a wee bit terrifying in their magnificence. But at the same time, such a dynamic blast of energetic particles hurtling our way could have caused major technological problems and electrical blackouts, like the event in 1989, which severely harmed Quebec's power grid, or a much earlier catastrophe that still managed to cause a lot of harm to the world. I'm talking about the Carrington event, which occurred in 1859 and was the first documented solar flare affecting our planet. It happened on the 1st of September and was named after Richard Carrington, the solar astronomer who witnessed the flare through his own telescope and sketched the Sun's sunspots. According to scientists, that flare was the most powerful documented solar storm over the last 500 years. The Carrington event triggered auroras that were visible as far south as the Caribbean. It led to severe interruptions in telegraph services all over the world, even shocking some telegraph operators and sparking fires after discharges from the lines ignited telegraph paper. Another major solar flare that erupted on the 4th of August, 1972, destroyed long-distance phone communication across a few states, including Illinois. This event even made the American Telephone and Telegraph Company redesign its power system for transatlantic cables. Now let's move to March 1985, when two super-powerful CMEs triggered a geomagnetic storm, which, in turn, set off a power blackout in Canada on the 13th of March. This blackout left around 6 million people without electricity for 9 hours. It is said that the flare disrupted electric power transmission from the Hydro-Quebec generation station and melted a few power transformers in New Jersey. And still, this solar flare was nowhere near the power of the Carrington event. The Bastille Day solar storm took its name from the French national holiday because it occurred on the same day, on the 14th of July in the year 2000. It was an X5 class event that caused some satellites to short-circuit and resulted in radio blackouts. It's still one of the most highly observed solar storm events. From October to November 2003, our star unleashed a series of large solar flares and coronal mass ejections, and they did reach Earth and slam into our atmosphere. Those solar storms, also known as Halloween storms of 2003, caused aircraft to be rerouted, impacted satellite systems, and led to power outages in Sweden. Besides, the Solar and Heliospheric Observatory couldn't fulfill its functions during this solar onslaught. On the 28th of October 2003, the Sun sent a whopper of a solar flare our way. The fire was so powerful it overwhelmed the spacecraft sensor that was measuring it. The sensor topped out at a whopping X28. But later, scientists figure out that the flare had reached a peak strength of about X45. One more thing that made the Halloween storms so scary was that they happened during a time in the solar cycle when solar activity is usually quiet. That's 2 to 3 years after the solar maximum. According to NASA's statistics, just 17 powerful flares erupted from our star during that time. The Sun spewed out another X-class solar flare on the 5th of December 2006. It was an X9 class flare that disrupted satellite-to-ground communications and GPS navigational signals for around 10 minutes. That solar storm was so powerful it even damaged the Solar X-ray Imager instrument on the GOES-13 satellite. It sustained damage to several pixels of its detector. In February 2022, SpaceX experienced the terrifying power of our star when a devastating geomagnetic storm destroyed 38 Starlink satellites worth tens of millions of dollars. It happened shortly after they were deployed. Unfortunately, Starlink satellites are especially vulnerable to geomagnetic storms since they're released into extremely low-altitude orbits, between 60 and 120 miles. They also rely on their onboard engines to overcome the drag force and raise themselves to their final altitude of around 350 miles over the surface of our planet. The thing is, during a geomagnetic storm, Earth's atmosphere absorbs energy from the storm, heats up, and extends upwards. It results in a denser thermosphere, which means more drag, and it can be a serious issue for satellites. That's exactly what happened. The batch of newly released Starlink satellites didn't manage to overcome the increased drag and started to fall back, eventually burning up in the atmosphere. The Earth, frozen and alone, exiled into deep space. Jupiter, the only remaining planet orbiting the Sun. No, it's not a premise for a disaster movie. It's one of many real scenarios scientists explored in their latest simulations. This time, the threat isn't the Sun swelling or a giant asteroid knocking planets into it like a cosmic bowling ball. It's something quieter and possibly already on its way. A recent study examined the potential consequences of a passing star coming too close. One such flyby could send planets crashing, flinging them into space, or mess with their orbits just enough to cause climate changes. But what are passing stars, and how likely is that to occur? Passing stars are normal stars, like our Sun, that move around the Milky Way. Since everything in space is always moving, sometimes stars pass near each other. Usually it's not a big deal. But if a star gets really close, its gravity can tug on planets like Neptune. That tiny tug can slowly change how the planets move, like a ripple spreading through the whole system. Scientists study these close encounters because, even though they don't happen often, they can have big effects over millions of years. They help us understand shifts in planetary orbits and how they may have shaped Earth's past. In fact, one theory suggests that a flyby 56 million years ago is what caused great climate change when Earth's temperature rose by up to 14 degrees Fahrenheit in just a few 100,000 years. That huge temperature jump changed life on Earth, leading to the evolution of some species while causing others to disappear. Even though it's impossible to prove whether there was a flyby a long time ago, we do know that events like this could mess with Earth's orbit in the long run. That's in the past, but what about the future? So far, we know that the solar system will have a close encounter with another star called Gliese 710 in about 1.3 million years. Gliese is moving towards us and is projected to pass within 10,000 astronomical units of the Sun. It won't come close enough to throw planets off, but it could still send icy comets from the Oort cloud our way, like a bored kid tossing a snowball without looking. One might hit something, but probably won't. However, in a recent study, scientists wanted to explore a more extreme scenario. What if a star passed even closer, say just 100 astronomical units from the Sun? That's about 100 times the distance from Earth to the Sun. From our point of view, it's almost unimaginably far, but in space, it's practically brushing shoulders. They ran thousands of long-term simulations covering up to 5 billion years of our solar system's future, and it turns out it doesn't take much. Just one close encounter can be enough to disturb the outer planets, like Neptune, and set off a slow-motion chain reaction that ripples inward. Over time, that gentle nudge can throw the whole system into chaos, a true cosmic butterfly effect. The good news is that even in this worst-case scenario, in 95% of simulations, the passage is nothing to worry about, and all the planets remain in place. However, in the remaining 5%, well, it's one disaster after another. The most frequent casualty in these simulations was Mercury. In nearly half of all unstable scenarios, Mercury ends up on a doomed path straight into the Sun. It's the smallest planet and the closest to our star, so it's especially susceptible to gravitational nudges, whether from the gas giants or from a disturbance rippling inward from a stellar flyby. When Mercury spirals into the Sun, you might think it's game over for the rest of the planets, but that's not always the case. Sometimes the system absorbs the loss and restabilizes, like an orchestra that keeps playing even after one violinist falls off the stage. Oops. Funny enough, Mercury already has a chaotic orbit, the most stretched and tilted of all major planets, and some studies already consider its fall into the Sun in the distant future inevitable. Now, Venus has a slightly better chance in these chaotic scenarios. It doesn't get ejected or swallowed by the Sun as often as Mercury, but it's far from being safe. Most of the time, the instability happens after Mercury goes rogue and disrupts Venus's orbit, nudging it into a slow-motion crash course with Earth or Mars. Even without the interference from field stars, long-term simulations show a tiny but real chance that Venus could eventually collide with Earth just from the way Jupiter affects Mercury. A Venus-Earth collision would result in both planets being completely destroyed. Oh well. A similar fate awaits Mars. According to simulations, in about 0.3% of cases, it either gets flung out of the solar system or collides with another planet. Mars is smaller and lighter than Earth, with weaker gravity, which makes it easier to knock it off track. What's interesting is that even in some cases where Mars is lost, Earth often manages to stay in place. Jupiter happens to be the heavyweight champion of the solar system, the proud owner of its own cloudy belts. Thanks to its massive size and strong gravity, it acts like an anchor, keeping everything else in check. There are 392 scenarios out of 12,000 simulations where all but one planet vanished, with Jupiter being the last one standing. Its stabilizing influence helps prevent smaller planets from going off course, and in some cases, it even helps the system recover after a disruption. Saturn, while less massive, seems to be Jupiter's loyal partner. But models show that when Saturn shifts its orbit abruptly, it can send gravitational ripples, known as secular resonances, straight into the inner solar system, nudging the orbits of planets like Earth and Mars. Finally, the most vulnerable ones are Uranus and Neptune. Sitting at the edge of the solar system, they're the easiest to knock loose, and in many simulations, they get ejected entirely. That loss sends gravitational ripples inward, disturbing the rest of the planets over millions of years. Even a tiny shift by 0.1% in Neptune's orbital distance can throw the whole solar system out of sync. The balance of gravitational forces would shift, forcing Jupiter and Saturn to readjust, which would push the disturbance toward the inner planets, destabilizing everything. Which brings us to the big question: what about Earth? While most simulated models leave Earth untouched, about 0.2% of the simulations end with Earth either colliding with another planet, Venus, or being thrown into the Sun. Out of 12,000 simulations, in 23 of those, Earth ends up as the only one still orbiting. But that's only if we don't include the Moon in calculations. With the Moon included, Earth becomes harder to predict. Our satellite could crash into Earth, get ripped away by a passing star, or destabilize our orbit over millions of years. Once again, this is a worst-case scenario, and while the odds are really, really small, it's not impossible. So, with that in mind, let's entertain the idea and see what would happen to Earth if it were to end up exiled from the solar system. Earth would become what scientists call a rogue planet, drifting through interstellar space with no sun to anchor it. The surface would quickly freeze, with temperatures dropping to hundreds of degrees below zero. But surprisingly, life wouldn't vanish completely. Earth's core would stay hot for billions of years, powered by radioactive decay and leftover heat from its formation. That heat could keep underground pockets warm. Scientists believe that this is the case with icy moons like Europa or Enceladus. Life might cling on in different caves or buried oceans. It wouldn't be a thriving world, but it wouldn't be completely empty either, at least for a while. Just cold, quiet, and alone. A ghost of a once lively world. And somewhere out there, maybe another civilization will look up, spot a faint blue dot drifting by, and curiously start running simulations of what might happen if this blue planet were to get really close, say just 100 AU from their sun.
A solar storm is crashing into Earth like a cosmic tsunami. First, the atmosphere ignites, sparking massive auroras. High-energy radiation slams into the surface, frying power grids, turning lights off across continents, and knocking out satellites. Planes lose navigation, radios go silent, GPS systems crash, radiation levels spike dangerously. Communication collapses, emergency services scramble in the darkness, and chaos spreads as people struggle to cope. Solar particles start to strip away the very air we breathe, slowly peeling off our atmosphere. Soon, Earth will become a harsh and hostile place. That's what solar activity can do to our planet and its inhabitants if we didn't have a protective shield called the magnetosphere. But even with this barrier, we're still in for serious problems. A mysterious 100-year solar cycle may have just restarted, and it could mean decades of dangerous space weather. New research suggests that the unexpected intensity of the ongoing solar maximum may be partly tied to a lesser-known 100-year solar cycle. If the Sun is indeed entering its villain arc, solar activity could spike even further in the coming decades. It means more solar flares, more chances of them messing with satellites, and way more of those crazy northern lights people keep posting on Instagram. Sure, not everyone's buying it. Some space nerds want more proof before jumping on this solar hype train. Let's break it all down into detail first. The sun goes through a kind of mood swing every 11 years. This is called the solar cycle. It starts off at a solar minimum, which is pretty chill, then slowly gets rowdy. We're talking sunspots, solar flares, and other fiery drama. Once we reach solar maximum, the situation starts to calm down again. The sun gets sunspots, dark patches on its surface, like the freckles we humans have, when its magnetic field starts flipping out. Literally, the sun's magnetic field completely flips during peak solar drama. Scientists track how many of these spots show up to measure how spicy the sun is getting. But wait, plot twist, there are other cycles too, like the Hale cycle, which occurs around every 22 years. This cycle controls how magnetic fields move across the sun. Plus, way back in history, there were moments when the sun basically went on Do Not Disturb mode. During the Maunder minimum, our star was basically in sleep mode for 70 years. In other words, the sun might be entering a new extra phase, and things could get dramatic. On the bright side, that means more auroras. At the same time, it could also cause issues for satellites, GPS, and other stuff we rely on. Ugh, let's just hope it doesn't mess with YouTube. This extra phase is called the Centennial Gleisberg cycle. It's basically the sun's once every 100 years I do something weird moment. Scientists think it messes with how intense sunspot cycles get. No one has fully worked out how this cycle works yet, but some low-key sloshing of magnetic fields inside the sun might be causing it. Yep, I did say sloshing, like a giant cosmic smoothie. A recent study from March 2025 claims that the CGC might have just hit restart. That could explain why this current solar maximum, the sun's drama phase that started in early 2024, is being so weird and unpredictable. How did researchers figure this out? They looked at something called proton flux. Basically, it's how many positively charged particles are flying around in Earth's radiation belt. There are 2 of these belts, shaped like donuts that wrap around Earth, full of particles from the sun. The thing is, when the sun is active, our upper atmosphere swells, which makes the inner radiation belt lose some of those protons. And when the sun is chill, proton numbers go up again. So those protons have been increasing for like 20 years, but just started to drop in the past year. Which basically screams, CGC has just hit minimum. Time for the sun to crank it back up. The data came from NOAA satellites that flew through the South Atlantic anomaly, which is like the Bermuda Triangle of space. It's this bizarre zone over South America where Earth's magnetic field is weaker and space radiation gets closer to Earth. This area is perfect for observing proton activity without sending a satellite into the actual danger zone. So, right now, we're probably nearing the end of the sun's current chaos phase, aka the peak of solar cycle 25. Back in May 2024, it hit us with one of the craziest geomagnetic storms in 500 years or so. And yes, that means super bright auroras lighting up skies all over the world, even in places that usually only get clouds and vibes. But the scariest thing? This wasn't supposed to happen. During the last cycle, the sun was oddly calm. So NASA and NOAA looked at that and thought that the next solar cycle would probably be the same. No biggie. Well, they were wrong. And they even admitted it. Now, scientists think that SC24's quiet phase was because of the Centennial Gleisberg cycle being at its low point. That probably made it the quietest sunspot cycle in 100 years. So now that SC25 is lit again, pretty literally, it might just mean the sun is back to doing what it normally does, being a little chaotic and wild. Recent studies think the CGC minimum is finally over. That would explain why the current solar activity is turning up the heat, and why the last one felt like a cosmic snooze. An even cooler thing is that a 2024 study used AI to analyze sunspot patterns and found that CGC might be messing with our forecasts more than we thought. And if this long-term mood swing of our star is really back on the rise, future solar cycles could be just as wild as the one we're in now, or even wilder. After all, we've just passed the CGC's low-energy mode, and we won't hit the next maximum for another 40 to 50 years, around solar cycle 28. That's a few decades away, but the sun's already throwing tantrums. The scariest part is that future solar activity might be twice as intense as what we're seeing now. You might be wondering right now, why should I care? Well, because when the sun freaks out, it messes with our stuff, especially in space. Satellites get dragged out of orbit because Earth's upper atmosphere literally puffs up like a marshmallow in a microwave when solar activity spikes. And this has already happened to a few spacecraft recently. And with tons of private satellite mega constellations like Starlink and its squad, the risk goes way up. There are some, even though those are few, that might not be ready for a full-blown sun rage event. Time to wear SPF 100 for your satellites. Astronauts are also at risk. More solar flares mean more radiation and more danger for humans in orbit. At the same time, more space tourists and missions mean more people potentially in the sun's cosmic splash zone. At the same time, not everyone is buying into the whole CGC is back and ready to party theory. Some experts say it's a cool theory, but we shouldn't get carried away. The thing is, the proton flux, those space particles we've been watching, only started dropping last year. That's not a lot of time. It might just be a short-term dip, like the sun sneezed and now everyone's freaking out. Also, we've only been able to track this stuff properly for 30 to 40 years or so, which is basically nothing in sun time. So there's no solid before and after data to compare CGC cycles and say, yep, this is definitely a pattern. Plus, the CGC itself is kinda mysterious. Like no one can fully agree on what it even is, how it works, or how much it actually messes with sunspot cycles. It's like the Bigfoot of solar science, blurry, weird, and causing drama in group chats. But even skeptics admit that the new study is interesting and well-intentioned, and that it might help us predict future solar cycles better. We just need more time, more data, and better definition of the CGC before we treat it like the ultimate weather app for the sun. In May 2024, stunning auroras adorning the night sky demonstrated all the power that solar storms emit as radiation. But sometimes, our sun does things that are far more destructive. I'm talking about solar particle events. During these events, blasts of protons coming directly from the surface of the sun can shoot out like giant cosmic searchlights. According to records, an extreme particle event hits Earth every 1,000 years or so. It often causes bad damage to the ozone layer and increases levels of ultraviolet radiation closer to the surface of our planet. Luckily, Earth's magnetic field acts as a powerful protective cocoon for our planet, fending off electrically charged radiation from the sun. In its normal state, this field functions like a ginormous bar magnet, with field lines rising from one pole, looping around the planet, and dropping at the other pole. This pattern is sometimes called an inverted grapefruit. This vertical orientation of the magnetic field at the poles allows some ionizing cosmic radiation to get through the field as far down as the upper atmosphere. There, it interacts with gas molecules and produces the glow we know as auroras. But over time, Earth's protective bubble changes. In the past century, the North Magnetic Pole moved across northern Canada at a speed of about 25 miles per year. Plus, it weakened by more than 6%. Even more shockingly, according to geological records, there have been periods of time as long as centuries and millennia when our planet's magnetic field was super weak or entirely absent. But we'll talk about those tragic times later. It's easy to imagine what our planet would look like without its protective bubble if you look at Mars. The red planet lost its global magnetic field long ago.
And once this field disappeared, most of Mars's atmosphere vanished too. In May 2024, a strong solar particle event hit the planet. It disrupted the operation of the Mars Odyssey spacecraft and made radiation levels at the surface of the red planet rise around 30 times higher than what a person receives during a chest X-ray. The Sun's outer atmosphere constantly emits a changing stream of electrons and protons, the solar wind. At the same time, the surface of the star also produces bursts of energy, mostly protons, during solar particle events. These bursts of energy have a connection to solar flares, extremely powerful bursts of electromagnetic radiation that can last from minutes to hours. Protons are way heavier than electrons and carry more energy. That's why they can reach lower levels of Earth's atmosphere, exciting gas molecules in the air. These excited molecules emit X-rays invisible to the unaided eye. Dozens and hundreds of relatively weak solar particle events happen during every solar cycle. Now, let's speak about solar cycles for a minute. You see, from a distance, the Sun seems to be calm and steady, but if you zoom in, you'll see that its surface is constantly seething and churning. It keeps transforming from a uniform ocean of fire to a chaos of warped plasma and back again in a repeating cycle. Every 11 years or so, the magnetic field of our star gets tangled up. Imagine a ball of tightly wound rubber bands. That's what it looks like at such moments. And then, at one point, it snaps and flips completely, turning the North Pole into the South Pole, and vice versa. Right before this event, the Sun steps up its activity. It starts to spit out giant blobs of fiery plasma, emit powerful streams of radiation, and grow planet-sized spots. This period has the name of solar maximum. It's a rather dangerous time for Earth, since it gets regularly hit by solar storms. Such storms have the potential to disrupt communications and damage power infrastructure. Even worse, solar storms can harm astronauts working in space and even make satellites crash into the planet. As the cycle ends, it fades back to the solar minimum, and then a new cycle begins. Anyway, back to our solar particle events. Researchers have found traces of extremely strong solar events happening throughout the history of Earth. And some of them were thousands of times stronger than anything our modern instruments have ever recorded. Such extreme solar particle events happen approximately every few millennia. The most recent one occurred around 993 CE. Beyond the immediate effect they have, solar particle events can kickstart a chain of chemical reactions in the upper atmosphere. And these processes often lead to depletion of ozone, which isn't a good thing. Ozone absorbs harmful solar UV radiation, which can damage not only our eyesight, but also the DNA of living beings. Plus, changing the amounts of ozone in the atmosphere can impact the climate. In a recent study, researchers used large computer models to examine how extreme solar particle events affect Earth. They found out that if a solar proton event arrives during a period of time when our planet's magnetic field is very weak, then ozone damage can last for 6 years, and the level of UV radiation might increase by 25%, boosting solar-induced DNA damage by around 50%. And apparently, this dramatic combination of a weak magnetic field and extreme solar proton events happens quite often. And some researchers believe that it may even explain a few mysterious occurrences in the past of our planet. For example, the most recent period of weak magnetic field started 42,000 years ago and lasted for around 1,000 years. This period included a temporary switch in the North and South poles. Several major evolutionary events happened during that time. For example, the last Neanderthals disappeared in Europe, along with the extinction of marsupial megafauna in Australia. Yeah, sadly, we won't see any giant wombats and giant kangaroos anymore. One more, even bigger evolutionary event might also be linked to Earth's geomagnetic field. Multicellular animals appeared at the end of the Ediacaran period, which started around 635 million years ago, and it occurred after a 26 million year period of extremely weak or even absent magnetic field. The rapid evolution of different groups of animals in the Cambrian explosion, about 539 million years ago, might have also been related to high UV levels and geomagnetism. The simultaneous evolution of hard body shells and eyes in multiple unrelated groups could have been necessary to detect and avoid harmful incoming UV rays. A complete reversal of Earth's geomagnetic poles might have a serious impact on the climate of our planet. Luckily, such flips don't happen overnight. The entire process stretches over thousands of years. Plus, even though the magnetic pole weakens during a pole reversal, it doesn't disappear completely. That's why the magnetosphere continues protecting the planet from cosmic rays and charged solar particles, even though there might be some amount of particulate radiation that will make it to Earth's surface. Our planet's magnetic fields are generated by moving electric charges. If some material allows these charges to easily move in it, it's called a conductor. Metal is a great conductor, and we often use it to transfer electric currents from one place to another. In this case, the electric current's negative charge, called electrons, move through the metal. The current is what generates a magnetic field. Earth's outer core is made of liquid iron and nickel. In other words, there are layers and layers of conducting material inside our planet. Currents of charges are constantly moving throughout the core, and the liquid metal is also moving and circulating there, generating the magnetic field. This magnetic field, in turn, produces something resembling a bubble around the planet. It's called the magnetosphere, and it's located above the uppermost part of the atmosphere. This layer shields and deflects high-energy cosmic ray radiation, which otherwise would be extremely hazardous to people and other forms of life on Earth. The magnetosphere also interacts with the ionosphere, the layer of our planet's atmosphere containing loads of ions and free electrons and capable of reflecting radio waves. The interaction between these two layers and magnetized solar winds is what scientists call space weather. The solar wind is normally mild, and there's no space weather whatsoever. Astronomers have discovered the most massive stellar black hole ever spotted in our home Milky Way galaxy. This newly found space monster is 33 times bigger than the Sun and sits 2,000 light-years away from us. Until recently, the largest stellar black hole found residing in our galaxy has been around 20 times as big as our star in terms of mass. As for the average stellar mass black hole, it's usually about 10 times as hefty as the Sun. Scientists from the European Southern Observatory's Gaia mission spotted the giant black hole after a star started to wobble while orbiting in that area. The black hole got the name of Gaia BH3. The proximity of this space object to Earth makes it the second closest black hole to our planet ever discovered. The nearest one is called Gaia BH1. It's hanging out around 1,560 light-years away from us. This uncomfortably close neighbor has a mass of about 9.6 times that of the Sun. It means that it's way smaller than the newly found black hole. Gaia BH3 is located in the Agila constellation. From Earth, it seems to have the shape of an eagle. Interestingly, astronomers didn't expect to find a high-mass black hole lurking so relatively close to Earth and remaining undetected for so long. Okay, we can probably admit that this stellar black hole is just a small fry compared to supermassive black holes like the one that dominates the center of the Milky Way. I'm talking about Sagittarius A star. This space giant has a mass of 4.2 million times that of the Sun. While a stellar black hole forms when a star collapses, supermassive black giants have their own ways of seeing the light of day. They are usually the result of mergers of progressively larger and larger black holes. We'll talk about that later. First, let's speak a bit more about how stellar black holes form. When stars near the end of their lives, they typically inflate, lose a lot of mass, and cool to form what we know as white dwarfs. Such massive stellar black holes as Gaia BH3 are believed to form when a star doesn't contain heavy elements and loses not so much mass over its lifetime. Such stars are called metal poor. Afterward, instead of cooling into a white dwarf, this star collapses into a black hole. The companion of Gaia BH3 is a very metal-poor star. It suggests that the star that collapsed and formed BH3 was metal-poor too. Astronomers know of about 50 stellar black holes in the Milky Way. Some black holes are larger than others. You see, the universe is filled with black holes. Some of them are sprinkled randomly throughout galaxies. Others, those giants we know as supermassive black holes, sit at the center of galaxies. While stellar black holes are usually just a few times bigger than the Sun, such space monsters can weigh from 1 million to 1 billion solar masses. But even though they're so much heavier than our star, they're packed into a relatively small area. On a cosmic scale, of course, the size of our solar system or so. Some astronomers think supermassive black holes could form by several stars colliding and collapsing at once, while other experts state that such space objects might have started growing several billion years ago. At first, a small seed appears somewhere out there in space, which then gradually increases in mass to form a black hole. This seed does it through the process of accretion, which basically means gathering more and more matter around itself. Besides the absence of any precise information about the formation of black holes, there's also the black hole information paradox. If a black hole has some mass, and as we know, these spaced objects have a lot of it, then, according to the first law of thermodynamics, it should have a temperature. And according to the second law of thermodynamics, it should also radiate heat. Stephen Hawking showed that black holes are supposed to emit radiation too. These days, this kind of radiation is called Hawking radiation. It should form at the boundary of a black hole, but after proving it, Hawking pointed out a paradox. If a black hole is capable of evaporating, some of the information it contains can be lost forever. The problem is that the information contained in thermal radiation emitted by a black hole gets degraded. It doesn't repeat any information about the matter swallowed by a black hole before. Such an irreversible loss of information contradicts one of the basic principles of quantum mechanics. Physical systems that change over time cannot create or destroy information. It means we must be missing something. Both physicists and mathematicians have tried to come up with different ideas, but they ended with pretty weird results. Some have even claimed that the universe could be holographic. It means that the universe that we know and love is actually the result of some mysterious interactions at the infinitely distant boundary. I told you, black holes are really strange. At the same time, we have definitely found space objects that seem to have the properties of black holes. For example, look at this image of black hole M87 star. It certainly looks like a physical object, but what if black holes don't exist at all? There's an idea that black holes are actually gravastars, a blend of gravity, vacuum, and stars. This theory was first proposed in 2001 by Emil Matola and Pavel O. Mazur. They hypothesized that at one point during the collapse of a large star, intense gravity might transform its matter into a new state. It's similar to what occurs when atoms are cooled to such low energy states that they start acting like a single superatom. When we speak of gravastars, a star might collapse to the point of the event horizon, or the point of no return, and then its matter is transformed into a new state. It exerts enough outward pressure to prevent the star from collapsing into a physics-defying singularity. In gravastars, an ultra-thin, ultra-cold, and ultra-dark indestructible shell surrounds heavily wrapped space-time. This new form of matter turns out to be very durable, but it's also a bit flexible, like a bubble. So anything that's trapped by the intense gravity of a gravastar and smashed into it gets obliterated and then assimilated into the shell of this bizarre space structure. One of the benefits of the gravastar theory is getting away with those messy paradoxes connected with information and singularities. But even though this idea sounds kinda cool, it doesn't explain the phenomena we observe. And we've definitely observed something that looks like black holes. On the other hand, look at this shadow. It isn't caused by the trapping of light in the event horizon. It's a slightly different phenomenon known as the gravitational redshift. It makes light lose energy when it moves through a region with a powerful gravitational field. So, potentially, it could be a gravastar. When the light emitted from the regions close to the alternative objects reaches our telescopes, most of its energy is already lost to the gravitational field, which causes the appearance of this shadow. And still, like with black holes, things get complicated when you add rotation to the equation. Many experts are sure that gravastars would not be able to remain stable during rotation. But wait, it gets even more bizarre. There are suggestions that the insides of gravastars could contain a series of thicker shells. Those are known as nestars, something like a matryoshka doll. Of course, these theories aren't perfect yet. Astronomers still have a lot of work trying to build functioning models. There's also a chance that both black holes and gravastars exist. But then, we've got another problem on our hands. How can we distinguish between the two? Some theories suggest that these different kinds of space objects should also emit very different gravitational radiation. It could allow us to figure out whether we're looking at a gravastar or a traditional black hole.
Electronic satellites suddenly go out of control. There are voltage surges across the globe. In some places, there's a complete blackout. Scientists have little data on this incredible solar behavior, so we're still unable to accurately predict how or when exactly the next geomagnetic storm will happen. One such event took place back in July 2012, but thankfully it missed us. Not by far, though, by a mere 9 days. Just to give you a glimpse of what nearly happened, I need to explain some astronomical basics. A solar storm is a series of effects we feel here on Earth after certain events occur on the Sun. Our star is nothing more than a huge ball of molten gases that are constantly moving around, so these events happen more often than you'd think. For a solar storm to begin, our Sun needs to emit bursts of energy. They're in the form of solar flares and coronal mass ejections. These two phenomena send electrical charges and waves of magnetic fields toward the Earth at an astonishing speed of about 3 million miles per hour. When these solar storms reach our planet, we can see northern lights display in locations close to the Arctic Circle. But they can also mess up satellites or other types of electronic communications. Some of these solar storms can be dangerous, and back in 2012, we came close to experiencing a very powerful one that could have had a serious outcome. The most powerful in as much as 150-plus years, based on research done by astronomers. But how did we manage to escape it? Did we have something to do with it, or was it just a pure coincidence? What we do know is that one of those coronal mass ejections did hit the Earth's orbit in late July 2012. Our planet had already left that specific location as it was on its scheduled trajectory around the Sun. So you might be asking yourself at this point, what if it didn't miss us? Turns out these intense solar storms are dangerous to all sorts of technological objects. Given we are now literally surrounded by electric objects, from our phones to our cars, try to imagine what would happen if they all stopped working all of a sudden. And here's how they work. Solar storms start with an explosion, or a solar flare. Then X-rays and UV radiation travel to our Earth at the speed of light. Some of the side effects? Well, they can include radio blackouts and GPS navigation errors. The effects can continue as minutes, or at times hours later, energetic particles reach our atmosphere. They move only a bit slower than the speed of light, but they can electrically shock the Earth's satellites and damage their components. Lastly, about a day later, clouds of magnetized plasma reach us as well. They can cause huge power blackouts, more or less paralyzing everything with an electrical plug. We might not even be able to flush our toilets, since most water supplies in cities use electric pumps these days. The effects of these geomagnetic storms would be different around the world, though. Solar storms are curious by themselves, but why do they affect some locations on Earth more than others? Based on recent research, geology has a lot to do with it. But I need to take you back a bit to paint you the bigger picture. Buckle up, because we're taking a trip in the time machine to a time when the moon didn't even exist yet. 4.6 billion years ago, our solar system looked a lot different than it does now, and that's putting it lightly. Hundreds of new planets began to form around the new sun. Planets like our own Earth, Venus, or Mars were still hurtling around the cosmos. Back in the 1970s, an astronomer named Donald R. Davis developed a theory that said the moon was born when another planet hit a newly formed Earth about 4.5 billion years ago. He also indicated that it might have been the size of Mars and later named this planet Theia. It's difficult to imagine what that impact might have looked like, even with the equipment we have these days. The astronomers suggested the giant impact hypothesis, trying to piece together this mystery. After running into our planet, the outer rocky layers of both Earth and Theia were projected into a circle of cosmic matter. Out of this debris, what we now know as the Moon was born. The Earth's core has apparently consumed Theia's iron core, that is, if it had any. Our planet also got into the position it occupies today. This way, it became more susceptible to geomagnetic storms. Back then, there was little to no information as to what might have happened to Theia, apart from giving us our only natural satellite. It took several years for a series of scientists to come up with an exciting new idea that revolutionized what we knew about our planet. What was left out of Theia is hiding under two continent-sized layers of rock deep within our planet. This theory is also one of the only explanations for why the moon is so dry and doesn't have much of an iron core. But why is geology so important when it comes to geomagnetic storms? Well, that's because recent data revealed that the type of rocks below your feet can affect how well your city adapts after powerful geomagnetic storms. Some types of rock, like sedimentary rocks for example, generally have more space filled with water, which makes them electrically conductive. Other types of rocks are denser and have more resistance when it comes to electricity. Whenever such a storm happens, people living in the New England highlands may have a higher risk of experiencing major disruptions. At the same time, those in the mid-Atlantic coastal plain have less to worry about, simply due to what's hidden beneath their cities. How did we know how scary these storms are? Well, this wasn't the first time it happened. Solar storms have dazzled the astronomer community for many years now. The most iconic event of this magnitude was the Carrington event, which happened way back in September 1859. It gave us a sneak peek of what the power of the sun is, to say the least. They named it after an English astronomer, Richard Carrington, who witnessed the solar flares himself. The power of that solar storm was something humans had never experienced before. The strong geomagnetic storm caused northern lights as far down south as the territory of Hawaii. On the morning of September 1, 1859, Richard Carrington made his way into his private observatory, located outside of London. He opened the observatory dome to have a complete view of the sky and directed his telescope to the location of the sun. He saw a bunch of huge dark spots that gleamed on the surface of our star. Shortly enough, Carrington noticed two enigmatic areas, intensely bright and full of white light bursting out from the sunspots. They disappeared 5 minutes later, but the effects carried on all across the Earth's surface. At first, later in the night, telegraph communications all around the world started to malfunction. Flashes of light started to burst from telegraph machines, disturbing the operators and even setting papers on fire. Brightly colored auroras started to appear in the nighttime skies all over the world, making confused birds chirp at night. Some people even began their daily activities, since they mistakenly thought the day had already begun. These days, our planet is laced with a mega information web, so the impact of such a solar storm would be even messier. Back in the 1800s, The telegraph system was just starting out, but this Victorian internet was an important way of sending news and private messages. Even in the United States, telegraph operators had noticed local interruptions because of thunderstorms and northern lights before. But the Carrington event and its effects were something they had never seen before. A lot of telegraph lines in North America became useless. One telegraph manager based in Pittsburgh even recalled that the currents flowing through the wires were so strong their platinum contacts were in danger of melting. Another example was that of a telegraph operator located in Washington, D.C., named Frederick W. Royce, who was hurt as his forehead touched a ground wire. Samples taken from the Earth's icy locations tell us that the Carrington effect was twice as big as any other solar storm experienced in the last 500 years. It's very difficult to imagine what the impact of a storm of that magnitude might be today. But based on a 2008 report drafted by the National Academy of Sciences, it might cost us between $1 trillion and $2 trillion in damages. There are things we can do individually to help reduce the amount of damage, though, like buying a generator or installing a backup energy supply. This can be either a solar panel or a wind turbine. More so, we can equip our houses with surge protectors that connect to our electrical panels and can save us from lightning and other power surges. The simplest solution of them all? Just unplug all the devices you're not using at any particular moment. If they aren't connected to a power source, they can't be affected by any surges.
For the first time ever, we saw the shape of a supernova explosion in real time. The blast was so immensely powerful that it was literally ripping the surface of the star right in front of our eyes. Now we can finally understand what actually happens inside a star right before it blows apart. You see, massive stars fight against their own gravity their whole lives. They burn hotter and hotter elements to keep themselves from collapsing inward. But eventually, the star starts producing iron in its core. And this is a problem. Unlike many other elements, iron doesn't create energy inside the star. So once this process starts, the star loses its support system and gravity wins. The core collapses inward insanely fast, and then everything around it crashes down toward the center of the star. Once all that falling material slams into the dense core, it rebounds and creates a gigantic shockwave, and that's what rips the star apart. Scientists didn't fully understand how that part worked, but new observations helped them. They could watch the shockwave while it was actually moving through the outer layers of the star. Even better, they could see the shape of the explosion, and it wasn't what anyone expected. The blast wasn't perfectly round. It was slightly stretched in one direction. It may sound unimportant, but it can actually change how we understand supernovas and their final moments, when a star suddenly releases more energy than our sun will produce during its entire lifetime. The exploding star was first spotted on April 10, 2024, by a system called ATLAS, which scans the sky for dangerous or unusual objects. Just a few hours later, scientists already pointed one of the world's most powerful telescopes, the Very Large Telescope in Chile, directly at the discovery. For a very short time, the star's real shape and the shape of the explosion were both visible. But soon after, clouds of superheated gas hid everything. The star was a red supergiant. That's an enormous star close to the end of its life, about 12 to 15 times heavier than our sun. Normally, when we think of a supernova, we imagine a giant flash of light illuminating space. That flash happens when the shockwave from the collapse gets through the star's outer layers and releases a truly enormous amount of energy. For many months, the explosion shines brighter than whole galaxies, but the first few hours are the most important, and usually impossible to study because they pass super quickly. This time, scientists used a special technique that studies how light waves move and scatter. It helped them notice that the exploding material looked almost olive-shaped. Later, the explosion slammed into the gas surrounding the star and its shape flattened. But it still kept the same overall direction even while it was expanding outward into space. That detail may actually help us solve one of the biggest mysteries about supernovas. Right now, scientists have two main ideas about what can actually cause a giant dying star to explode. The first idea claims that tiny particles called neutrinos blast out from the collapsing star and heat everything around them, but the heating happens unevenly. So, the explosion becomes messy and unstable. That's why the star blows apart in a rough, uneven way. There's another theory. It sounds much more extreme. Some scientists think that the star sends out enormous streams of energy from deep inside its core right before exploding. These streams work like giant cosmic drills. They punch through the star and force the explosion outward in a more organized direction. The new supernova can tell us which idea is closer to the truth. The telescope data showed that the explosion had a very clear shape and direction almost from the very beginning. It didn't look random or chaotic. The blast stayed surprisingly symmetrical while it expanded through space. And that's a big clue. The explosion looked more like something fueled by powerful streams of energy rather than a messy neutrino blast. This discovery changes a lot. For decades, researchers have been arguing over what really happens inside a massive star during its final seconds. And now we can finally figure out the mechanism behind those gigantic explosions. And if you think that all supernovas happen insanely far away from Earth and don't affect us in the least, let me tell you this. Right now, Earth is drifting through the leftovers of a giant explosion that happened somewhere in space a very long time ago. And scientists just found some proof inside ancient Antarctic ice. Researchers were studying ice that had formed up to 80,000 years ago and discovered tiny traces of something called iron-60. You see, most iron on Earth is a normal version called iron-56, but iron-60 is different. It's radioactive, extremely rare, and it slowly disappears over millions of years. And it usually forms during supernovas. In simple terms, scientists found microscopic pieces of star ash frozen inside the ice. At first, researchers were confused. The Antarctic snow where they discovered this kind of iron was less than 20 years old. It made no sense. If a nearby star had exploded recently enough to spray this material onto Earth, we would have definitely noticed this. The sky would have lit up with one of the biggest cosmic explosions in history. But there was no supernova. This meant something else was going on. Eventually, they figured out the truth. Apparently, our entire solar system is currently moving through a gigantic cloud of gas and dust. Scientists call it the local interstellar cloud. For years, researchers suspected that this cloud may have formed after one or more huge stars exploded nearby a long time ago. And now, the discovery of iron-60 proves this idea. The material likely came from an ancient supernova that once sent its radioactive debris across space. Even after all this time, tiny particles from that explosion are still floating through our region of the galaxy, and some of them are literally falling onto Earth. To test the idea, scientists dug into old deep-sea sediments and ancient Antarctic ice cores going back 30,000, 40,000, and even 80,000 years. And every deeper layer gave them more evidence. The levels of iron-60 changed over time exactly the way they would have if Earth had been slowly drifting through a giant cloud filled with ancient supernova debris. And its microscopic radioactive particles have been falling on our planet for thousands of years. By the way, iron-60 was extremely difficult to find. Scientists started with around 660 pounds of Antarctic ice. After processing it, they started searching through trillions of atoms to spot just a few tiny traces of iron-60. But the search paid off. Researchers are sure that this ancient stellar debris may help us better understand the strange clouds surrounding our solar system. We can also learn more about the powerful cosmic events that had been affecting our galaxy before we even existed. Now, it might come as a surprise, but many of the elements you're made of come from supernovae. It can be anything, from the oxygen you breathe to the calcium in your bones. The iron in your blood or the silicon in your computer might have first appeared in the core of a star. And when a supernova exploded, it unleashed a storm of nuclear reactions, which in turn produced lots of building blocks making up the world around us. Supernovae are like giant particle machines in space. When a star explodes, the blast wave crashes into the gas around it and creates a super powerful magnetic storm. Tiny particles get trapped inside, bounce around, and speed up to insane speeds. Eventually, some of those particles shoot across space as cosmic rays. And then, some of them hit Earth. They slam into our atmosphere, smash into our atoms, and create invisible showers of particles that rain down on us all the time.
One of the biggest stars we've ever found is wobbling on the edge of disaster. And it won't go quietly. It might collapse in on itself and instantly become a black hole, or explode in a blinding supernova. It might even crash into its companion star, and we could probably see it. The star in question, WOH G64, wow, that's a mouthful, I'll nickname it Jerry. So Jerry is a red supergiant. These are huge stars at the end of their lives. Like cosmic seniors, they've already burned through most of their fuel, puffed up to an enormous size, and are getting ready to explode as a supernova. They're cooler on the outside than many other big stars, that's why they glow red instead of blue or white. Still, the biggest and brightest of these stars are kind of a mystery. Astronomers aren't totally sure what happens to the most extreme ones right before they explode. When they look at the sky, they don't see as many ultra-bright red supergiants blowing up as they would like to. Instead, they see hints that some of them might change color and heat up again before the end. One famous example is our star called WOH G64 in the Large Magellanic Cloud. That region is basically a stellar nursery. It means it's packed with thick clouds of gas and dust where stars are born. It's the perfect place to grow something extreme. Now, for decades, we considered Jerry one of the most outstanding red supergiants ever found. It's enormous, it's incredibly bright, like me, and losing mass like crazy. It's also surrounded by so much dust that it looks heavily wrapped up, like it's hiding inside a thick cosmic blanket. But recently, something weird happened. The star's light signature started to look completely different, as if this red supergiant had changed identity. Now scientists think Jerry isn't just a single star. It's probably a rare pair of stars locked together in a relationship called a symbiotic binary system. In this system, the red supergiant seems to have transformed into something hotter and more unstable, called a yellow hypergiant. Now, yellow hypergiants are like the middle phase before total destruction. They're enormous. Some are so big you could fit billions of suns inside them. But they don't last long. This stage is brief and chaotic, like a star pacing nervously before its final act. Yellow hypergiants are extremely rare because they represent a short transition between the red supergiant phase and the final explosion. We know of only a few dozen confirmed examples. Now, why would that transition happen? One possibility is stellar drama. Ooh, what could happen? Well, as we know, Jerry isn't alone. It likely has a companion star. The two may have interacted so intensely that the red supergiant blew off a huge chunk of its outer layers. Imagine two stars spinning around each other so tightly that one basically starts stealing material from the other. That lost material could have formed a massive cloud, a shared envelope that briefly swallowed both stars. But there's another possibility. Even without interference from a companion, a star this massive can become unstable on its own. It might have gone through a huge eruption that lasted more than 30 years and is now settling down into a hotter yellow phase. Whatever it is, this is incredibly rare, like watching a star evolve in real time instead of over millions of years. In any case, after watching this monster star suddenly change before their eyes, astronomers now think it may be getting close to the end. A new study claims the star could be on the verge of exploding in a massive supernova. Or, since it's so unbelievably heavy, it might skip this step completely and collapse straight into a black hole. Now, Jerry was discovered about 50 years ago and labeled a red supergiant. It has about 30 times the mass of our Sun. But the really mind-blowing part is its size. If you drop this star into the middle of our solar system, it would stretch all the way past Jupiter. Stars like this live fast but not long. Jerry is only about 5 million years old, That might sound ancient until you remember our Sun is 4.6 billion years old and still going. The problem is, massive stars burn through their fuel super fast. That's why they shine so bright, grow to ridiculous sizes, and then go out in a blaze of glory. Now, we don't know how it'll happen, but because of its enormous mass, Jerry's demise won't be quiet. In cosmic terms, it could happen soon, meaning within a few hundred to a few thousand years. It might explode in a supernova, blasting its outer layers into space. Or it could collapse inward so violently that it forms a black hole on the spot. There's even a chance it could eventually slam into its companion star. So let's say our red supergiant tears itself apart in a supernova. Then we need to learn more about these space fire shows. Supernovas are gigantic explosions that happen when massive stars finally collapse. They're incredibly important to how we understand the universe. Astronomers use certain types of supernovas, like measuring sticks, to figure out how far away galaxies are. In fact, it was supernovas that tipped scientists off in 1998 that the universe wasn't just expanding, it was actually speeding up. But there's one problem. Even though supernovas are powerful and bright, they happen incredibly fast. Catching the exact moment a star explodes is like trying to photograph a lightning bolt at the exact second it strikes. But an international team of astronomers says they managed to do exactly that. They got the earliest and most detailed look ever at a supernova right as it was blowing apart. Using the European Southern Observatory's Very Large Telescope, they basically watched the shockwave from the collapsing star blast through its surface. For the first time ever, they could actually see what shape the explosion had. And that shape does matter. When a massive star runs out of fuel, things go bad fast. For millions of years, the star balances two forces: the nuclear fusion in its core pushing outward, and gravity pulling inward. But once the fuel is gone, gravity wins instantly. The outer layers crash inward, slam into the collapsed core, and rebound outward in an intense shockwave. That shockwave tears through the star and blows it to pieces. The result is a supernova. That's the basic idea. The details of how that shockwave forms have been hard to pin down, because supernovas are nearly impossible to catch in the act. Out of the trillions of stars out there, astronomers would need to be already looking at the exact right star at the exact right moment. And it would have to be close enough to study before expanding gas clouds block the view. This time, they got lucky. The explosion happened about 22 million light-years away, which also means it happened 22 million years ago. Think about that. Astronomers spotted it quickly and managed to start observing it within just 26 hours after it was first detected. In supernova terms, that's incredibly fast. They used a technique called spectropolarimetry, basically a way of studying how light is scattered and how its vibrations are aligned to figure out the shape of the blast. What they found was surprising. The explosion wasn't perfectly round. Instead of expanding like a smooth sphere, the shockwave stretched out slightly, more like an olive than a ball. When the blast slammed into the gas surrounding the star, it flattened, but it still expanded evenly along that stretched shape. It means the very first light and material didn't shoot out evenly in all directions. The explosion had structure right from the start, and that structure gives clues about what was happening deep inside the star when it collapsed. Now, here's another interesting fact. The star that went supernova was a red supergiant, about 12 to 15 times the mass of our Sun. And based on how many red supergiants are out there, astronomers expected to see lots of them exploding. But for years, they didn't see many. It was almost like these giant stars were disappearing quietly. More recent observations from the James Webb Space Telescope suggest they probably are exploding. We just couldn't see them clearly before. Maybe because dust and gas were hiding the blasts. And now, this new observation suggests their explosion might actually follow a common pattern, with a clear stretched shape rather than a perfect sphere. In other words, these cosmic explosions may be more organized than we thought. What if the Sun went boom? Well, you can guess it would be super bad news for us. this was sure a short video, huh? Nah, wait, I have more. If the sun blew up, chaos would ensue in our solar system. But scientists tell us that it will certainly happen one day. But why? How exactly would events unfold? And is it possible for us to somehow survive this event? Hey, let's delve into it. First of all, get ready for a journey to the sun's core. The sun's heart is packed with hydrogen atoms, having an out-of-this-world dance party. These atoms are so excited that they smash into each other with all their might. And when they collide, something magical happens. It's called nuclear fusion. And in this fusion fiesta, the hydrogen atoms combine to form helium atoms, a chemistry experiment on a grand scale. During this nuclear fusion, a teeny bit of mass from the hydrogen atoms is transformed into a massive amount of energy. It's Einstein's famous equation E equals mc squared coming into play. Energy is unleashed in the form of light and heat, radiating outwards to brighten up the entire solar system. And once all these processes get going, a bunch of energized particles called photons join the fun. These photons are like tiny packets of light, bouncing and zipping around in all directions. They play a crucial role in carrying the sun's energy through space, illuminating our world and warming our cozy planet. But to keep all this going, so that atoms don't escape and create complete chaos, the sun's core needs to be under tremendous pressure. This pressure comes from the immense weight of the sun's outer layers pressing down on the core. The outer layers are squeezing the inner core. But the inner layers don't give up. The energy created from fusion and the bustling photon party tries really hard to escape the sun's core. But the core is so dense, like me, and the pressure is so big that the energy takes its sweet time to make its way out. It bounces around, gets absorbed, and re-emitted by other particles. Eventually, after a long time, it reaches the sun's surface and zooms off into space, reaching us as sunlight. So now you know how the sun works. Now, what happens once it reaches the end of its life? Well, here's the twist. Our sun has a limited supply of hydrogen fuel. In about 5 billion years, it'll run out of its fuel. After that, the star will undergo some big changes. Now, pay attention, because there's a pretty good chance we're all going to miss this. First, the sun will puff up and become a red giant, exploding like a balloon. It will grow so big that it will swallow up the inner planets, including our beloved Earth. Talk about a sun taking up all the space. So we won't even see the end of our sun unless we move somewhere further away. After the red giant phase, the sun will shrink a bit. Its outer layers will fade away into space, leaving behind a beautiful planetary nebula. It'll be revealing its glowing core. Ooh! The core, now filled with helium,
will start sounding weird.
And will start fusing heavier elements like oxygen and carbon. These reactions won't be as energetic, like a party with less dancing and more chill vibes. Eventually, even the helium will be used up, and the sun will become a compact white dwarf, a stellar retiree enjoying its retirement home. Scientists estimate that the sun has about 7 to 8 billion years left before it dims its lights. Don't worry though, by that time, humanity might have traveled to far-off galaxies, or maybe even evolved into amazing space beings. So our sun won't go out with a bang like fireworks. It's not big enough to become a supernova or a black hole. Those stellar superstars need way more mass than our sun to pull off those cosmic tricks. But what if it blew up very suddenly, just like an abrupt event without any reason? Well, let's see. Imagine this. The sun goes boom, and Earth is in for a wild ride. The event unleashes an insane amount of energy, sending a shockwave racing through space at the speed of light. It takes about 8 minutes for this shockwave to reach Earth. Why? Well, the sun is a whopping 93 million miles away from us on average. So it takes a little over 8 minutes and 20 seconds for the sun's light to travel all that distance and reach us. But let's talk about the event itself. It would be a great sight to witness, but sadly, it would also be the end. Roll credits. The crazy amounts of unleashed energy would cause the sun to expand rapidly, again swallowing up the inner planets, including our Earth. And that's not all. Brace yourself for a massive burst of radiation. the sun would unleash a torrent of supercharged particles. We're talking about X-rays and gamma rays, the kind that can seriously mess things up. When these high-energy particles hit the atmosphere, they go wild, causing all sorts of chaos. They ionize the atmosphere, creating a ginormous electromagnetic pulse. This pulse is like a shockwave for electronic devices. It fries them, zaps them, and leaves them useless. So if your gadgets aren't protected, they're in for a rough time. Speaking of rough times, after that, it's instant vaporization for our planet. But the sun's grand finale just doesn't mess with Earth. It wreaks havoc on the entire solar system. That massive burst of energy would be crashing into everything in its path. Planets and other objects get knocked off of their cozy orbits, causing chaos and unpredictability. The asteroid belt between Mars and Jupiter, kapow! It's gone, obliterated, or scattered to the cosmic winds. And even planets that will survive this event will probably go off their orbits to wander somewhere. And let's not forget about the outer planets, like Jupiter and Saturn. These giants generate their own internal heat, which keeps them cozy and attracts lots of moons. But the sun's boom would steal their warmth, turning them into incredibly cold places. And now that we've discussed how catastrophic all this would be for everything in our solar system, let's ask the logical question: can humanity make it? The short answer is nope, we wouldn't make it. Everything would be wiped out, except maybe some sneaky bacteria hiding in the shadows. But in a crazy scenario where the sun gave us a heads up about its plans, we might have a fighting chance. If we knew in advance and had time to prepare, we could get our survival gears turning. So what could we do? Since Earth itself won't survive the sun's tantrum, we'd have to move somewhere. Remember how we mentioned that not all planets would be completely destroyed? Well, sadly, the ones closest to the sun, Mercury, Venus, and Earth, would disappear. So the easiest option would be to move to some other solar system with its own Earth-like planet. But what if the Earth somehow managed to survive this catastrophe? Let's not think about how it happened and just discuss the consequences. Well, our climate would go crazy. During the first moments of the sun's kaboom, the radiation and particles would crank up the temperature big time, like a never-ending heat wave. We're talking major greenhouse effect. The oceans would evaporate, creating thick, fluffy clouds that trap heat and refuse to let it escape into space. And after that, without the sun's warm embrace, the Earth would quickly become an icy freezer. So we'd have to think outside the box. One idea would be to take shelter deep underground, where we won't be that much affected by radiation and sudden temperature changes. As you dig deeper, the temperature rises. So, with the right tools and resources, humanity could hunker down in fortified bunkers, surviving for a couple of years without the sun's rays. Why just a couple of years? Well, remember how we said the sun is a gravity center of our solar system? Without it, Earth would be adrift in search of a new center of gravity. Imagine our planet, our trusty satellite, the Moon, and all the other planets slowly floating away into space. Luckily, our trusty sun is hanging in there, keeping us warm and shining for many more cosmic adventures to come. So, we're safe for a few billion years. But it's always fun to imagine impossible scenarios. So stay tuned for more what ifs.